Okay, thank you very much, David. It's a real pleasure to be here. The first time in the IOP building. In my entire tenure as editor, it's been through the pandemic, so I was really glad to meet all of you and enjoy the talks today. All right, so this is a talk about strange metals. But before I begin, I realize I should explain a non-strange metal. So an ordinary metal like copper or gold is well described by a standard theory going back to Boltzmann and then extended to quantum mechanics by Landau. And the general assumption of the theory is that the electrons, although they can interact with each other strongly, most of the interaction is simply a renormalization of the electron into a quasi-electron. And once you have done that renormalization, the quasi-electrons are essentially independent and they scatter with each other very rarely. So the typical scattering time blows up as 1 over temperature squared. So at low enough temperatures, this scattering time is extremely long, and the theory is self-consistent. So one of its predictions is, for example, the resistivity of a metal with a few impurities will have a t-squared dependence to its resistivity. So now you can ask, what is the temperature at which Boltzmann theory will break down? When can it break down? And you look at the internal consistency of the theory, you find that there is this time that's now being called the Planckian time, because it's made up of nothing but Planck's constant and temperature. And as long as the time tau is bigger than the Planckian time, the theory is internally consistent. And so now you see that if you just have to make temperature low enough, no matter how large the interaction is, there's always a low enough temperature, but this time tau becomes longer than the Planckian time. So that would mean that the Boltzmann-Landau theory is always applicable. And indeed, that was found to be the case for a long time, and everyone was very satisfied with the state of affairs. So I was a young postdoc when these materials were discovered that we just heard about a couple of talks ago. These are the high temperature superconductors. This is yttrium, barium, copper-oxide. And these have critical temperatures for superconductivity up to 100 Kelvin. And I didn't know this, but Commonwealth fusion system was also mentioned by Professor Speller, where these Repco magnets are being used for fusion. So anyway, so that's enough motivation. That wasn't the original motivation, but that's really wonderful that these materials we've been fascinated about for so long could, in fact, be very important technologically. Anyway, so if you now look at what happens above TC, which is the focus of my talk, then out here at higher doping, where the TCs are relatively low, you do find that the Boltzmann-Landau theory basically works. But the strange metal is up here, and that, in a sense, is the most interesting region because that is the region of the highest TCs. So immediately you now see that you can't apply the usual Bardeen-Cooper-Schrieffer theory to this metal to understand the onset of superconductivity, because the assumption number one of Bardeen-Cooper-Schrieffer theory is we have an ordinary metal, and then we ask how it undergoes an instability to superconductivity. So we can't directly apply it. We can't apply it at all to even get an estimate of where TC is. Anyway, so that's really the heart of the problem that many of us have been grappling with for over 20, nearly 30 years. So what is strange about the strange metal? Well, this is, of course, the celebrated result, also shown earlier today. The resistivity is linear function of temperature. I think Pierce showed that. And as I just reminded you, in an ordinary metal, this should be T squared. But in this talk, I want to focus on slightly more complicated observations, which are the optical conductivity. So this is by measuring the reflectivity or transmission coefficient of these superconductors. You get some frequency-dependent conductivity. And in the traditional Drude theory, you would write it in this form, or the Boltzmann theory, where m star and tau would be frequency independent. But very generally, you can write any conductivity by some causality relation in this form, where m star and m m star and tau are frequency dependent. So here's the full frequency and temperature dependence of the conductivity. These are the magnitude and the phase. And then you can take this data and consistently extract from it some frequency dependent m star and a frequency dependent tau. So if you do that, I just show the data for tau, for example. You see some very remarkable things. You see that tau, h1 over tau, is linear function of temperature. And also it's a linear function of frequency when frequency is bigger than temperature. And this is summarized in this plot or this formula right here. Tau of omega, SA at omega equals 0, is just of order h power over kT. So that's precisely the lower bound at which Boltzmann theory cannot be applied. So you need some other theory. And furthermore, the frequency dependence here is, the natural frequency scale is not any intrinsic energy scale of the system. You might think that it should be somehow some exchange coupling or some other parameter in the Hamiltonian that determines the natural frequency scale. What's remarkable is just temperature itself. So everywhere, in fact, nowhere in this expression is there any dependence on any material parameter. So this is observation. This is the observation that shows this, and there are many other similar observations. This is what people are now calling Planckian dynamics. So anyway, so that's the heart of the problem, which I wouldn't say have fully solved, but I want to talk about some recent progress in trying to understand this this curious behavior. All right, so I'm going to begin with the SYK model. So this was in a different version, was a model that I came up with my first graduate student, Jean Moulier, in 1992, when the data wasn't this good, but it was already clear at that time, it was very much motivated by the cuprates and the breakdown of the Boltzmann-Landau theory. And I was looking for a simple model which would, have behavior, at least this behavior here, somehow have a time which is just given by temperature and nothing else. It's independent of the strength of the interactions. And the word entanglement didn't exist then, but today we would say, Boltzmann theory neglects the entanglement between the electrons. So we want a state of the many electron system which is strongly entangled, which is also a metallic state. We don't want a spin liquid of the type that Nandini was talking about, because that's an insulator. We want a metallic state that can exist at arbitrary density, which would have a strong entanglement. Okay, so this was improved by the same Kitaev that Nandini mentioned to a much simpler model, but the original model had essentially the same properties, but I'll describe the simpler model. So here's one version of it. So imagine you have a bunch of sites at which electrons can sit, so I just occupy a fraction of them with electrons. I'm going to ignore the spin here. And now I'm going to allow these electrons to move around. And the one rule I'm going to impose is that no electron can move on its own, that there is no single electron hopping process. You can put it in later, but once you put in single electron hopping, then the system eventually at low enough temperatures, Boltzmann and Landau win, and you go back to the usual behavior. So we just turn off single particle hopping for now, just so that we can understand electron entanglement better. So now we want these electrons to move around. So let's say there's some amplitude for electrons on site 11 and 12 to hop to site 5 and 14. And in quantum mechanics, any such process that's allowed has a complex number or an amplitude associated with it. So you give me a complex number, which I write here, and that's one parameter in the Hamiltonian of the system. And then there's order n to the fourth other processes, each of which has a set of complex numbers, a complex number associated with it. And really, you have to give me all of them, give me a table, and all of these processes happen together. It's they're not in sequence. Schrödinger's equation will evolve and allow these processes to interfere with each other. That's really crucial. That's that interference between collisions of electrons that entirely neglected by Boltzmann's equation. We have to put the interference back in. All right, so this is an extremely difficult problem, because the size of the Hilbert space grows exponentially with n. And so when n, biggest you could do is about 30 today, and the best computers in the world, classical computers. But we want to understand n of 100 or 200, forget about 10 to the 23. There's just no way to solve this problem. Okay, so what was the advance to be proposed already in 1992, 93 was the following. Well, this is some set of numbers. Allow me to assume that they are uncorrelated random numbers. That's all. So you give me a table of numbers, and if I just look at them, they look kind of random. There's no particular pattern. So I'm just going to assume they're uncorrelated random numbers. That's it. And then amazingly, you can use the power of randomness to solve the problem essentially exactly. We solved it at n equals infinity. Today, with the help of powerful mathematical technology brought to bear by string theorists, you know a lot about even the finite n corrections away from n equals infinity. But already at n equals infinity, this model is extremely interesting. At least we thought it was very interesting in 93, and you'll see why we couldn't convince too many people that it was interesting then. Anyway, eventually its time has come. So this is the model written down in explicit notation, if you want, in terms of fermion operators. All right, so how do you solve it in the large n limit? In fact, the simplest way to see the solution is just to put a Bayesian theory in U alpha, beta, gamma, delta. So you can write down some Green's function, and if you draw some Feynman diagram, this is the kind of Feynman diagrams you draw at order u squared. And all you do now is you average each term to all orders in u, but you average the term by term. So for example, here, if you average using the fact that the u's are uncorrelated, these indices alpha, beta, gamma, delta are independent. And so then when you sum over all the indices, you get the term of order u squared. In contrast, when you look at this graph, it's down by a factor of n. So this particular graph, now sometimes called the melon graph, is the only one that survives. You have to sum all melons and melons within melons and so on. And you can also add another melon over here and so on. So the sum of all of these graphs, it's an infinite set, so it's a non-perturbative solution, is just the solution of these equations. This is the Dyson equation, and this is the equation representing the melon graph, and it has to be solved self-consistent. So when I wrote down these equations in 92, I thought, well, someone solved this. This is too simple to not have been solved. We looked around, nobody had ever looked at it. And then we said, well, okay, it'll just take us a few weeks to understand everything about it. So we did understand a few things, but we were still understanding new things about these very simple looking equations. Now, hiding inside them is in fact aspects of quantum gravity, which I'll hint at that, why that's the case, but we understand. So I think now we have a pretty good understanding of the structure of these equations and why they're related to quantum gravity. Okay, I'll say a little bit about it. Okay, so from the solution of this equation, we learned a lot, and I'm not going to go into all the technicalities. But what you can show from the solution is that this is a model that has no single particle excitation. So it doesn't have any ions, it doesn't have electrons, it doesn't have anything. It just has, it's basically a system that has no quasi-particle-like excitation. So how do you get, what are the excitations? Well, they're complicated. They're just a complete rearrangement of the wave function. The many-body wave function is huge, and to go from one state to the other, the wave function just changes chaotically in this huge space. And so the way it carries current, well, is some kind of entangled mess. That's the best I can say. But we can compute quite a few things. Now, of course, this thing, it doesn't carry current. It's just everything is hopping everywhere. There's no space. But if you extend it with space, this is what you find. So let me just highlight two basic properties. One, and this is something that was understood a bit later by George and Parcolet. They proved it, and we suspected this was the case already in '93. That it, in fact, has exactly this type of Planckian dynamic. So the amazing thing, if you took this model and you perturbed it a little bit, and then you ask how long does it take to thermally equilibrate, you'll find that provided you don't perturb it too much, the thermal equilibration time is just h power over kT. And it's completely independent of the value of this coupling constant u, which is the mean square value of the interaction. That doesn't come in at all. And that's entirely, that's completely different from the Boltzmann equation. And the Boltzmann equation, everything depends on the collision term. And all relaxational processes depend on the rate of collisions. It doesn't appear here. The collisions essentially become universal and very quantum. Okay. Then the other property, which also we understood with Parcolet and George, was a bit disappointing. This model turns out to have a zero temperature end. And that seemed, rather bizarre, and it's not to us. It almost seemed like a violation of the third law of thermodynamics. Now, the third law of thermodynamics really involves the other opposite order of limits, and that would imply some exponentially large ground state degeneracy. This model absolutely doesn't have it. So here's actually the answer, which kind of anticipated, but now even this function is known. This is the density of states from actual numerical diagonalization. And you see the states are very, very dense down to the ground state. There is no degeneracy, but there's lots of states, and there's enough states at very low energy that this particular limit is non-zero. So the entropy density does not vanish as temperature goes to zero. All right, so anyway, so we found this result, and it seems rather strange. There's certainly no experiment on the cuprates or any other material had ever shown anything like this behavior. And that's probably why after 2001, we kind of stopped working on it. We shouldn't have, but anyway. So that was 2001. And then around 2010, I started to learn more about black holes. And it turns out there are certain types of black holes called extremal black holes, which have a net charge or they're rapidly rotating. And they have exactly the properties that are present in the SYK model. In particular, they have some relaxation times, which is just h bar over kT, where now T is the Hawking temperature. And they have an entropy which doesn't vanish as temperature goes to zero. In fact, this result is in one of Hawking's original papers. I didn't know about it in '91. Anyway, so that seemed, yes?
Temperature has an H bar in it, and you have an H bar in it, which is sort of...
That's a peculiar thing, which is now much better understood.
Right.
Right, so the relaxation time of black hole is a purely classical thing, something that Vishweshwara computed using Einstein's equation. However, if you express it in terms of the Hawking temperature, which has an H bar in it, then it's just this very simple expression. And that's intimately connected to why classical gravity is dual to a quantum system in one higher dimension. That's the ADS-CFT correspondence. That's how H bar appears in ADS-CFT also. I should speed up. How much time do I have?
10 minutes.
Okay, great. Yeah, all right. So this is just for pure entertainment. I know nobody cares about black holes, but this is how I didn't care about black holes, but slowly I started caring when it was they looked exactly like XYK models. And this, in fact, immediately had a very strong implication, which is that the black hole degeneracy that Hawking had computed had since then been mapped to a black hole entropy, had since then been mapped by string theorists to an actual degeneracy due to supersymmetry. And so this shows, no, that's not how it should happen when you don't have supersymmetry. There's just an exponentially dense set of states. And the SYK model is really was the first model which provably you can show that there's an exponentially dense set of states down to zero energy generically, without any fine-tuning or anything like that. Anyway, so there's been a lot of progress since 2010, especially since Kitaev's simplification of the model. And now the whole function is known. So the density of states of a charged black hole, this is the Bekenstein-Hawking result. It's just the area of the black hole. And then this cinch factor, that's the smooth function cinch of energy. That came out from all the studies of the SYK model. And then this final prefactor in recent work involves actually knowing something about what's actually inside a black hole. Anyway, enough of black holes. Let's get back to cuprates. All right, so now it should be clear anyway. The SYK model is at least good for black holes. Is it any good for cuprates? That was the original motivation. I was trying to find some model which had at least some inkling of behavior that looks like the cuprates. But it's not reasonable to apply the SYK model directly to cuprates. First of all, it's zero dimensional. It doesn't have any space. And secondly, it has this huge entropy. Charged black holes may have that entropy, but cuprates definitely don't. So in the last few years, we think we've made progress. Many people have thought about such questions. And one way to approach it all is really in the context of a more general theory of quantum phase transitions of metals, which Piers also mentioned in his talk this morning. So going back to the phase diagram of interest, you have the strange metal above the high TC superconductor. What else do we have? Well, we have the blue region, which I've already told you was the ordinary metal. And here we have a pseudo gap, which I won't say very much about. So it's another phase, which is not as mysterious as the strange metal, but is more like a spin liquid of the type that Nandini just talked about, but also has some additional mobile electrons in it. So one way you could characterize these metals is by doing a photoemission experiment. And in photoemission, you can measure what's called the Fermi surface, which is, loosely speaking, the boundary between the occupied and unoccupied states in momentum space. So this is the Fermi surface of this particular region, where the states inside are occupied, the states outside are empty. This is Kx and Ky. And these are states on the square lattice of YBCO, say. Okay, and so now it turns out that this Fermi surface is exactly what you would expect in the Landau theory of electrons and metals. It encloses an area which is proportional to the density in precisely the way that you expect. So it works extremely well. On the other hand, if you go to the pseudo gap, you see these strange Fermi arcs, as they're called. And it seems like whatever it is, you have a different type of metal, which has a very different Fermi surface and many other properties that are also different. All right, so the point of view I'm going to take now is that the heart of everything is the quantum transition between these metals. Now, you rightly say, well, where is this quantum transition? At low temperatures, we have a superconductor. So I'm going to just say, well, forget about the superconductor, even though it's the most interesting thing. And imagine a world where the superconductor wasn't there. And then you would have, in principle, a quantum phase transition between these two metals. And let's try to, as theorists anyway, try to understand this quantum phase transition. And maybe one of the properties of quantum phase transitions is that it's unstable to superconductivity. That would be step 2, but I'm not going to go to take that step today. But can you, by this picture of some hidden quantum phase transition, understand what's going on in the strange metal? All right, so this is a question that many of us, point of view that many of us have taken, and I want to give you an update on the status. So how do you describe such quantum phase transitions? Well, in the simplest, in every case that we look at, in addition to the Fermi surface, you have to introduce a scalar field, a Bose field, phi. Now, this could represent some broken symmetry. That's the case. I'll show you some examples. Phi could be some autoparameter of broken symmetry, but it could also be one of these emergent anyons that Pierce and Nandini have mentioned, which carries additional emergent gauge charges. So I won't go into those details, but in any case, no matter what kind of exotic or non-exotic quantum phase transition you talk about, this is like a minimal ingredient. You have a Fermi surface and a scalar field, and there's some coupling between them, which I'll write down in a bit. So what are some examples? Well, one example is some kind of what's called an Ising nematic transition, where there's a deformation of the Fermi surface. Here, the Fermi surface goes from being almost circular to being kind of rectangular. And that breaks the symmetry between the x and y direction. Or there can be what's called a Fermi surface reconstruction, where this region has antiferromagnetic order. And the case of most interest, I believe, for the cuprates is a case where this is a more exotic state, which has coexisting spin liquid with mobile electrons. And that also is in the same general structure. In this case, phi would be this so-called slave boson that Pierce introduced. Okay, so a lot of work has gone into studying all these three types of quantum phase transitions of metals. And I won't go into all of the details, but let me just pick one of them, say that the simplest one, where phi is just involves the deformation of the Fermi surface. And this is the kind of theory you want to work with. You have a Fermi surface of fermion psi, then you have some scalar field, which is described by some kind of Landau-Ginzburg theory that you use in the Landau theory of phase transitions. And then you have this Yukawa coupling, where the fermions scatter off phi fluctuate. Anyway, so there's been a lot of effort to try to understand this by a variety of methods. You can also apply these SYK-like methods by giving these fermions fake flavor index and then allowing these couplings to be random. But that's not really necessary. There's also other methods that people have used. And there's general agreement that this actually is very interesting in 2 dimensions. Right at the phase transition point, the quantum phase transition point, you do get some very strange state of matter, which has no particle-like excitations. However, one shouldn't declare victory, as many people did for a while, because when you actually study its transport properties, when you see how current flows in this system, you find that the absence of quasiparticles actually doesn't make much of a difference. There were claims that would give you all kinds of strange behavior in the conductivity as a function of frequency and temperature, but they weren't correct. And the key point is that is what's called drag, that the fermions are scattering off these bosons very strongly so that the electron quasiparticle breaks down. But eventually, any current that was being carried gets back to these, because of momentum conservation, gets back to the fermions. So the conductivity really is actually infinite, even though there are no particles. So this is not, of course, what's seen. The resistance of the strange metal is quite large. Despite almost 2 decades of work, we've come to a disappointing conclusion that this doesn't work. All right, so what do we need? Well, what we claim is that what you need, so this is the same points that I just made. Sorry. You need to put in impurities. This shouldn't be a surprise from the talks you've heard today. Impurities control not only the resistance of ordinary metals, so why shouldn't they be so important, any less important for strange metals? All right, so let's put in impurities to the theory of quantum phase transition. Again, a topic that's been studied a lot, but we think we've made significant progress in recent years with the help of many collaborators mentioned here and these papers. Okay, so I'll go back to the theory. of a quantum phase transition in some metallic system. And now I want to put in some impurities. So how do you put in impurities in the theory of metals? Well, you put in some random potential that scatters the fermions. So V of R is some fixed spatially random potential, which comes from the impurities, maybe the oxygen atoms moving around. And then you average over those impurities, and that's what leads to the theory of disordered metals ordinarily. Eventually there's weak localization corrections and Altshuler Aronoff corrections and so on. And there's a huge amount of work on this starting from the 80s, 90s. And it's a very well understood subject, also tested in experiments on many, many metals. Okay. So could this be the most important thing? Well, it turns out no. These effects are present even near the quantum critical point, but there's much more serious effects to worry about. And those have to do, one way to account for these other effects is to also put in randomness in the coupling between, in this case, between the fermions and the boson. So what does this coupling do? Well, this coupling effectively changes the position of the quantum critical point. So if I go back to this phase diagram here, there's a critical coupling for the phase transition. So it could be that this part of my sample is to the left of this coupling. The other part of my sample is to the right of this coupling. So that kind of inhomogeneity is the most important thing to include. And that leads to very singular effects, not on the fermions, but on the bosons, and then consequently on the fermions. So in fact, the most important effect of disorder, as we are now discovering, is not to localize the fermion, which is what generally assumed in the theory of disordered metals, but in fact to almost localize the bosons. So that's the key thing here. All right, so you put this random coupling. I'm sorry, this is a bit more technical for many of you in this audience, but hopefully I've explained everything in words. And then you go ahead and solve this theory. Well, that's easier said than done, but we have learned so much on how to solve the SYK model. And basically the bottom line is the first thing you do is you just do the same kind of diagrammatic expansion that you did for the SYK model to this theory by the usual tricks of making couplings random in flavor space. Anyway, so you get some set of graphs that you have to solve, very similar to the graphs that we solved 92, 93. And in fact, you get, lo and behold, almost everything you need. You get the linear T resistivity, you get the Planckian time, you get a T log T specific heat, and so on. But all of these properties are sensitives in varied degrees to the degree of disorder, not just on the potential scattering, but also the disorder in the interactions themselves. Now you can ask, why should there be disorder in interactions? After all, the interaction is Coulomb interaction. How can they depend on space? Well, remember, you were talking about a strongly interacting system. And so if I start with something like the Hubbard model, where you would expect the U to be the same everywhere, but the hoppings can be very different because of impurities. Well, if you renormalize down a little bit, then you're dealing with something like a TJ model. The exchange coupling J is T squared over U. So the renormalized couplings, like the exchange coupling, can certainly be space dependent because they depend on the hopping and the wave function of electrons, and not just the Coulomb interaction. So that's really the origin of this G prime, but exactly understanding what determines G prime in the cuprates is really an open problem. And so I was very delighted to see that there's all this experimental work on really looking at influence of disorder on the cuprates, and I hope there'll be much more. All right, so in this model where we just treat the disorder in this simple self-consistent way, as I've already claimed, you get lots of very interesting properties. For example, you can have the resistance linear in temperature right near this critical point over here. There's also an instability to superconductivity, which I haven't mentioned. This is the observation of the optical conductivity. These are our calculations. And they look very similar. This was the scaling of scattering time. And this is what we see in this calculation. Okay, so that all works very well. But I just mentioned that happens in this very mean field-like treatment. But we can now ask what happens at very low temperature where you can't do this mean field treatment of this random Yukawa coupling. And so one other way to diagnose this is to look at the eigenmodes of the boson. So you have this disordered system, you look at the eigenmodes of the boson fluctuations. So there's various ways of doing that in certain large N calculations or in a paper that just appeared today on the archive using quantum Monte Carlo. And what you find in both calculations is that if you're at somewhat higher energies, this is a measure of the localization length of the bosons. The bosons are quite extended. They look somewhat like this. But when you go to lower energies, they become very localized. And we also understand, roughly how that happens, but don't have time to go into that. So why am I mentioning all this? Well, let me now show you somewhat older data of Nigel Hussey's group of, again, the resistivity, in this case, lanthanum, strontium, copper-oxide. And here, the red regions is where the resistance is linear in temperature. The blue region where the resistance is quadratic in temperature. So you do see this quantum critical fan. I was showing you much higher temperatures earlier, which is described by this SYK-like theory. But what Nigel and others have seen in other materials too, this was sometimes famously called the foot. This is the famous foot right here of an extended region of linear resistivity. And this recent paper by Avishkar et al., and also our more approximate calculation of the large N limit, we think we understand the origin of this foot. And so the summary is that there is a regime at higher temperatures where bosons and fermions are both extended, and you can really apply some kind of self-consistent average theory to describe the transport. Whereas when you go to very low energies and low temperatures, you have localization of the bosons. These are these overdamped bosons, sort of like two-level systems in glasses. But whereas the fermions remain extended. Of course, eventually the fermions will localize, just as due to Anderson localization. But I think that's much lower temperature. It's not relevant for the observations. But much before that, the bosons localize, and that's really what's giving you this foot that you see in many experiments. Anyway, so there's a lot to do to try to really understand this picture better, and also hopefully experimentally see some signatures like these different type of bosonic excitations in some kind of mesoscopic experiments. That's really what we hope will happen. Anyway, so just to summarize, perfect timing then. Okay, so what is the SYK model? It's just it's really the simplest and first solvable model of a many-body system that has no particle excitation. No, not even electrons or any fractionalized excitation, anything else. Everything is strongly entangled so that particles make no sense. And if you now extend this zero-dimensional SYK model to 2 dimensions, it's given us a start to understand. It certainly matches observations, but now we need to understand better what the origin and source of this disorder is. And then, quite surprisingly, at least from the point of view of 92, when I didn't even know what a black hole was, there's a dual mapping of the original SYK model, fortunately for me, to exactly what's needed to understand the low energy properties of certain category of black holes in 3+1 space-time dimensions. Thanks.
At the end, you said about going to mesoscopics, and you had that.
Yeah.
That boson disorder.
Yeah.
So what's that typical length scale? Is that atomic or points?
Yeah. This is, well, I mean, so I would say, yeah, this is a few lattice spacing. So yeah. So this, I think it's 100 by 100 grid of atomic size. Yeah. Of that order. Yeah, these pictures are from our papers early this year. This paper just appeared on the archive. It's a better paper because it's It doesn't make the larger approximation, but has very similar results. Yeah, so, and it's a more microscopic model. So, yeah, I don't have those pictures here, but it's of the same order. So what we claim is that it's really happened that this is energy, or you can think of as temperature. If you go into this graph, if you were to look here at these temperatures, then the boson modes will all be extended. So we're looking at some spin fluctuation spectrum, local spin correlations. There's nothing very special. There are no localized low energy modes. But when you get down here, you will see these two-level systems emerge at low temperature. It's a collective phenomenon. That's what we claim. So, yeah. So it's on the scale of a nanometer or so, and maybe if you can measure dynamic spin fluctuations. Again, the energy scale is a few Kelvin, so it's kind of difficult. Yes.
Two short questions. Very beautiful in the talk. One is about sigma xy, the transverse you tried.
Yes, of course.
The one is whether your theory could keep the K of dependence.
The K the K meaning what?
In the normal state.
No. So this theory definitely.
The K dependence, in principle, your theory does not change, but.
The K dependence is fully included in these graphs. So basically, it's sort of like the way you do, weak localization theory. You have an electron which has a dispersion, and then it scatters over random impurity. It gives you some elastic scattering rate, and then you average over impurities. All of that. So in fact, this is the average over interaction. So here is very, very similar. The full K dependence is there, but there are also random interactions. You keep them both. You have to keep them both. So one of the lessons of this calculation is that you just put in impurity, then you find you can get some very singular behavior in this electron self-energy, but you find Fermi liquid transfer. But if you put in randomness in the interaction and just do the same calculation, then you get a strange metal transport. To get strange metal transport, it's really crucial that there be some randomness interaction. That's the main message of all of these papers. And then your first point, indeed. So this team of really good people, we are working extremely hard on computing the magnetoresistance and the Hall effect in these kinds of theories. So I'm not going to claim any results yet, but I promise you will have something to say soon.
If you put disorder in the Yukawa coupling or in the electron-electron interaction, you would also generate random mass disorder for the boson.
That's exactly. I skipped that part. Yes. Normally, the way you put Harris disorder is random mass disorder.
Yes.
So,
but my question is, you have different localization length, right, for bosons and fermions. So how could you test by playing with microscopic disorder to push together apart the different localization length? I mean, how to have a knob that acts predominantly as interaction disorder rather than random mass disorder for the fermion, for example?
Yeah, so I think that's a great question. I'm not sure if I have a very good answer as yet. But certainly the physical claim is that at these low temperatures where you're seeing strange metal behavior, the electrons are not localized perfectly. They're scattering a lot and they have some very random waveforms, but they're not local. But there are lots of low energy localized bosonic excitations with energy of order kBT. So if you were to do some very local probes of dynamic spin fluctuation spectrum, for example, as a function of position, you would see local resonances in some regions, but not other. So that's the claim. But your question really is, how do you do an experiment where you tune random V, but not random G? Yeah, I'm not really sure, but my initial guess would be, point-like disorder is more affecting V, but a disorder that's more, change in density over a given region, maybe coming from out of plane disorder, not in the plane, is more likely to have an effect on random mass, which is the same as random G. In fact,
Yes.
you can rescale what we don't really. This we discussed this in this PRL just about to appear. You can put a random mass term here, but just by rescaling phi, you can put it over there.
Mhm, yes.
And that's equivalent to saying that you're working with the exact boson eigenstates. That's why it's much better to put it there, because then your perturbation theory is in terms of the exact boson eigenstate, at least low order. Eventually, the localization of boson takes over. That we cannot describe analytically. That's only comes from our numeric work.
Yeah, I actually have several, but let me ask just one, given the time of interest. So let's just go back to SYK without even bosons.
Yeah.
You call them metal, but no particles. So
Well, in the sense that, let me quickly answer that question. Sorry. So there's this parameter Q, which is the density. You can vary Q continuously. The solution exists for a whole range of. That's why I meant by metal. It's compressible.
metal by compressible and not necessarily.
And if you took a lattice of these and you couple them together, you would get metallic band.
And your bosons not necessarily have to be a vector, right? Not a spin bosons or
Could be anything.
Can I be a density?
Yeah, so that's the other beautiful. Yeah, so that was, thank you. All right. Where did I say this? Yeah, so here, this is a remarkable thing. When you don't have disorder, there's all these different universality classes, depending on whether it's a vector or not a vector, whether it's finite momentum, zero momentum, which have all been well classified, these different Hertz-Mills classes. Once you put in disorder, they all become the same. This is disorder, the Harris disorder, meaning not random field disorder where you break the symmetry or whatever that was driving the transition. That's a whole another ballgame. We haven't thought about that. But when you put in Harris disorder on all these three types, they all flow to the same universal behavior. And that's also, I think, very nice because it's, I believe, the type of underlying quantum phase transition that apply to the pnictides to the one I apply to cuprates are very different. But if you look at the strange metals, they're very, very similar. And that's another, I think, a nice feature of this theory.
Yes, can you tell us anything about superconductivity? So, why is this state unstable? Towards superconductivity? Indeed, the highest CC.
Well, if I knew the answer to that question, I'd be writing that paper. No, I think what the rough answer is, near a quantum phase transition, I think most people would agree with this. Near a quantum phase transition, this coupling between the bosons and fermions becomes, very, very strongly effective. Unlike the electron-phonon coupling that comes with a gradient, it's a very weak coupling. And so that electron-phonon coupling, as you know, has two effects. Electron-phonon coupling leads to an electron lifetime, which is very long, so you don't worry about it. And also induces an attraction between the electrons, which leads to superconductivity. So here the coupling G similarly has very similar effects, but it's strong in both directions. But it seems to be stronger in the scattering sense. And that's why you get a strange metal. So it's very strong and scatters the electron and gives you, in fact, the electron quasiparticle ceases to exist. But it also induces a coupling that's attractive between these non-quasiparticles. And eventually, even in this theory, that does lead to superconductivity. We know that. But I wouldn't say we have any reliable way of estimating TC. The final superconducting state is smoothly connected to the usual BCS state. It's not an unusual state in the sense that all the quasiparticle quantum numbers and the symmetry broken is exactly the same as BCS. So in that sense, BCS theory is correct. But BCS theory also has in it the transition from the superconductor to the normal state. And that transition is not described.
Okay, here's a question. We'll say the last question, but probably one line to bit. Press you a tiny bit more, but the future of you.
The Hall effect.
The appearance of T squared
Yeah.
fallout lipid immediate effect
Yeah.
feature suggests something that's not Planck, something that has a scale to T squared over W. People have tried to estimate that scale. So doesn't that suggest you need another element beyond the current theory, which is scale invariant?
Yeah, so there is, so in the theories we've been looking at, we have to worry about the bandwidth of the normalized particle. That does come in. But it would be simplistic to say we have two relaxation scales. That's not, these are complicated integral equations of frequency, and we have to understand a bit better of how the solutions work. I mean, even to get the linear resistivity here, I mean, it can be done, but it's not something you don't do a Boltzmann-like calculation. It's closer to what kind of calculation that's in Franke-Kadanoff. Franke-Kadanoff, so very much that. And so we're trying to extend Franke-Kadanoff to include the Hall concept. Not simple, but let me say, this has been very much on our mind. It's the problem we want to solve. We haven't solved it, but the bandwidth of the fermion does play a role.
Comment.
Yeah.
Subir, I think you showed us inhomogeneous SYK model.
Yeah.
Because your power will give us.
Yeah.
It does not say the clean system will not give.
Well,
So my logic.
no, it is saying that.
It's a clean system also see linear thing.
No, I claim they're not really clean. I would say, no, we are saying that, so this is what we are saying. If you take a perfectly clean system, then you will get you can get a non-Fermi. You can break, if you do photo emission, you can be broad, and non-Fermi liquid behavior. But if you have a perfectly clean system, the non-Fermi liquid behavior will not give you a strange metal. In fact, it gives you a perfect metal. The transport will be Fermi liquid. That's what we do. Okay. That is definitely, certainly what is also correct is any model that anybody has solved in a clean system to give you a non-Fermi liquid, all these papers here have shown does not. There have been many more claims that it does give you a strange metal. Essentially, all those papers are wrong. Now, I can go into some details why and why many famous people wrote wrong papers. Maybe I did too. That was a while back. But certainly after the cuprates, people were saying exactly what you said. I have this model that gives you a huge self-energy, and therefore it's a non-Fermi. I'm sorry, all of those papers are just, I didn't say that. So those are wrong, and they're wrong because of the following.
Actually, I mean experiment. If the clean sample, experiment show linear resistivity.
Our theory, then with the whole, then all these papers here are wrong. I don't think it's possible. Well, so one, I can give you one piece of evidence in support. So there's twisted bilayer graphene, which shows all these exotic phases for the twisted bilayer graphene. And then they also claim some strange metal behavior. Now, twisted bilayer graphene is actually quite disordered, despite all their claims. Not that old. On the other hand, Andrea Young has untwisted graphene, multi-layer, where he has very similar phases, rhombohedral graphene. That's much, much cleaner. And he sees the same phases, but he does not see things. So anyway.
Yeah, I hope there we go. So thanks all round from all of the attendees online to all the speakers as well. So the last couple of questions from online. In relation to the black hole entropy connection, what aspect of multi-particle quantum entanglement in the SYK corresponds to the event horizon that essentially defines a black hole?
All right, that's a wonderful question. I don't have the slides to explain. I have a whole another talk where I explain this. All right, so this is the explanation very quickly. So here's a black hole with an actual event horizon with a net charge. And very naively, you would say, in the presence of this black hole, I have to do the path integral in 3 space and 1 time dimension of the metric of space-time and the gauge field. This is the calculation that Gibbons and Hawking did in 1977, but they just took the saddle point. When they take the saddle point contribution, you get the Bekenstein-Hawking entropy. So now we want to look at the correction to this. Now it turns out what happens is that for charged black holes, because of the peculiar nature of the black hole metric, the low energy modes that correct this, the leading correction, comes from the radial directions only. So in the low energy theory, you have to only consider one space direction. You forget about the x direction, one space and time. So you have a 2-dimensional theory now, and the horizon is this one point. Okay, that's the point. All right. So you have a theory in one space and one time. Now there's a beautiful principle of quantum gravity that it's holographic. And so this means that, there's some across the horizon, the origin of the entropy is it's an entanglement entropy across the horizon. So now that your space is just one-dimensional, all your entanglement is at one point. And that entanglement at that one point, which is really a sphere here, because it's the 0 angular momentum mode. So the entanglement on the surface of a sphere considered as a point, that is what's described by us. I'll leave it at that. So that expressions I gave for, there's 2-dimensional reductions. One is a purely classical dimensional reduction where only the 0 angular momentum mode of a charged black hole matters. That's Einstein. Hawking certainly knew that. Well, that's not but then you get a theory of gravity in one space and one time, and that becomes exactly what that turns out. To solve that is exactly what the SYK model is, exactly what the doctor ordered.
Okay, thank you. One final one from online, and then we will wrap up. So regarding excuse me if I mispronounce this, scalar field, scalar field pi or phi, that exhibits the sharp change in its expectation value as a function of the parameter s. Can it be thought of as arising out of Cooper's pairs?
Short answer is no. So here's a picture. In fact, you could view this line as the expectation value of phi at 0 temperature. That's not what I've drawn. We ignore this TIN. So as you're coming from this side, phi is 0. It has a non-analyticity. It doesn't jump, and phi is going up. So here the assumption is that the underlying physics, first thing we need to understand is the strange metal. And phi is what's driving the creation of the strange metal. And the superconductivity is just an afterthought. It's another thing the phi does, but superconductivity itself, I don't think that's going to drive it. I don't know of any mechanism how that's.
Thanks, Subir, once again. Thank you, Subir.